Welcome back to another video. I've got some time here, at least a half an hour, so that's plenty of time, if not 45 minutes or so. So we're going to keep going on this book. We're about we're almost a third of the way through, so that's some good progress. So let's keep going. We can take a data set composed of sentences from a particular language of our interest, train a model where we randomly mask words from such sentences, and train the encoder-decoder to predict which is the missing word. Somehow we are training the network to learn how the language works, the internal rules that determine the relationships between words, and the most likely word at a specific position. This is called a language model, and one of the consequences of this language model training is that we now obtain a compact representation of the input data. This is referred to as embeddings in the context of natural language processing. Somehow, the vector in this latent space represents a set of properties of the word that is coding. We could think of such properties as: is it a noun? Is it an object? Is it a quality? Is it large or small? Etc. In reality, we do not know exactly what those properties are because they are automatically computed, and we have no easy way to know their individual meaning. However, one fact is that semantically similar words will have a similar vector representing them in such embedding space. This is precisely what we wanted, a solution to represent the input words, but that somehow took into account some level of semantic awareness. We can now use the encoder portion of the above network as an embedding layer that will transform the input raw word vectors from the dictionary into a more meaningful representation that we can use for other use cases. As we see in the example below, in a possible latent space with two dimensions, D1 and D2, the terms EVPN and VPLS, which are clearly highly related, would appear closer. Remember, distance is measured based on the angle between two vectors. In contrast, the term Amazon would be further away from both, but must be closer to Microsoft because both represent large tech companies. So here we've got D1 and D2, which I assume stand for dimension 1 and dimension 2. And then we've got latent space, which we remember from before. We were talking a lot about latent space. I don't really remember what latent space is. So let's get a quick refresher on that from ChatGPT. So I'll go back to the one I was using before, this one here, and I'll say, give me a refresher on the concept of latent space. All right, ChatGPT needs to think for a bit. We're using the paid version, version 4 here. Should have some reading pretty soon.
The concept of latent space is fundamental in many areas of machine learning, particularly in models that involve significant data compression and transformation, such as autoencoders and generative models. Here's a detailed explanation. What is latent space? Latent space refers to an abstract, multidimensional space where each dimension represents latent variables. These are features of factors that are not directly observed but are inferred from the data. In machine learning, especially in fields like deep learning, latent space provides a compressed representation of the input data, capturing the most essential aspects needed for a particular task, such as classification, regression, or generation. Key characteristics of latent space: dimensionality reduction. Latent space is typically of much lower dimension than the original input space. This reduction helps in extracting and retaining only the significant features of the data, discarding noise and redundant information. Data compression. By mapping data to a latent space, models effectively compress data. This is particularly useful in tasks like image compression, where reducing data size without losing critical information is key. Feature learning. The process of learning a latent space involves discovering the underlying patterns or features that best describe the data. These features are not manually engineered but learned from the data itself. Improved interpretability. Although latent spaces can be complex, they often allow for a better understanding of data relationships and dynamics by focusing on key variables and their interactions. How latent space is used in machine learning. Autoencoders. In an autoencoder, the encoder compresses the input into a latent space, and the decoder reconstructs the input from this latent representation. The latent space here captures the most critical features of the data necessary for reconstruction. Generative adversarial networks, GANs, and GANs. A generator model creates new data instances from noise introduced in the latent space, aiming to mimic the distribution of real data. The latent space serves as a source of variability and creativity for the generator. Variational autoencoders, VAEs, unlike standard autoencoders, generate a latent space that is modeled explicitly as a probability distribution, typically Gaussian. This allows sampling and generating new data points from the learned distribution. Dimensionality reduction techniques, methods like PCA, principal component analysis, and TSNE, T-distributed stochastic neighbor embedding, also explore the concept of latent spaces by mapping high-dimensional data to lower-dimensional spaces to reveal hidden structures. Applications, image processing. In tasks like image denoising, compression, and super-resolution, understanding and manipulating latent spaces allows models to perform effectively while using less computational resources. Recommendation systems. Latent factor models and recommendation systems use latent spaces to represent user and item features to predict user preferences. Natural language processing. Models like BERT use latent representations to understand text, capturing contextual meanings that improve performance on a variety of NLP tasks. Understanding latent spaces is crucial for designing and interpreting models that rely on complex data transformations. It's a core concept in achieving efficient and effective pattern recognition, data compression.
Sorry, my mind wandered during all of that. I really just, I don't know, something about this just makes me zone out and daydream. So I really wasn't listening to the explanation. Can you explain latent spaces in a way that's like latent spaces? Can you explain that concept in a way that will keep me engaged as someone who's having trouble remembering this because it's just like boring me to death? All right, it's got to think. I think it's because this conversation history is so expansive, it takes a lot longer for it to generate. Party analogy?
Absolutely. Let's try a more engaging and straightforward way to understand latent spaces by using a fun analogy. Latent space explain. The party analogy: imagine you're at a big, bustling costume party, and you're trying to quickly describe the scene to a friend over the phone who can't be there.
Oh, that's interesting.
The party scene, data. Each guest at the party represents a piece of data.
Right.
Some are dressed as pirates, some as superheroes, others as mystical creatures, etc.
Exactly.
Your quick glance, encoder, you take a quick look around and decide to summarize the party by the types of costumes you see.
Right.
You notice key themes: lots of capes, some swords, a few wands, and some scary masks.
That's brilliant.
Describing over the phone, latent space, instead of describing every single guest, which would be too much information and very boring for your friend, you decide to mention only the key themes you observed. This summary is your latent space. It's a compressed version of the party scene, capturing the essence, main features, without going into every little detail.
My jaw is dropped.
What do you focus on? Dimensions of latent space. Your focus areas: capes, swords, wands, masks, act like dimensions in a latent space.
Wow.
Just like you chose to focus on the significant costume elements, latent spaces in machine learning focus on the most important features of the data.
That's
your friend
brilliant.
imagination, decoder, based on her summary, your friend imagines the party. If your description captured the essence well, their mental image will be pretty close to reality. In machine learning, this is what the decoder is. It tries to reconstruct or understand the data based on a simplified latent description. Why is this useful? In machine learning, especially in tasks where dealing with huge amounts of data directly isn't practical, like processing thousands of photos or large texts, latent spaces help by boiling down the data to its most meaningful features.
Right.
This makes processing faster, less resource intensive, and often more effective. Real-world example: Netflix recommendations. Netflix uses something like latent space to recommend movies. It looks at the big picture of your watching habits, your party, and summarizes it into what genres and movie features you like most.
Yeah.
Then, it uses this summary to figure out what other movies with similar features you might enjoy. This approach to understanding latent spaces turns a dense topic into a more relatable concept. By connecting it to everyday scenarios or common experiences, the idea becomes less abstract and more tangible, hopefully keeping the boredom at bay.
That was absolutely brilliant. So yeah, latent spaces, if you're at a party, someone calls you and they say, hey, I'm able to go to the party now. I thought I was double booked, but I can go there. What kind of party is it? I don't know that much about it. So you look around the room, there's people all dressed as pirates, and you say it's a pirate themed party. Even though somebody in the room doesn't have a costume on, somebody is dressed as something else, doesn't look like a pirate. Pirates nowadays are from Somalia and don't look anything like, they don't wear the same kind of, so they're not dressed like actual modern day pirates. Um, Not all pirates are from Somalia, but I hope that makes it clear. Is the latent space is the distilling down of the details into a meaningful descriptor where the other person on the phone understands how to fit into this party. So if they come dressed as a pirate, as they understand it, they will be fitting into the party very well. So it's the same for recommendations. You see somebody watching, it's like genres too, like the horror genre. Like, what does that even mean? Some horror movies are so garbage they're not scary at all. Some horror movies absolutely are terrifying. And then even with that, you've got subgenres. You've got a psychological thriller. You've got a slasher. You've got different kinds of subgenres within that. So thank you, ChatGPT. I never would have understood that without that analogy, and I really understand it now. So let me see what it has to say about this graph. That's kind of what I've been doing. So remember, adequate data representation is one of the critical success factors of many machine learning project. The missing an S. Oh, of any. Okay, I've read that wrong. Of any machine learning. So adequate data representation. Embeddings are a fundamental piece in that task in the context of NLP.
The image you uploaded shows a 2D representation of a latent space with vectors representing different concepts: EVPN, VPLS, Microsoft, and Amazon. This visualization helps illustrate how concepts might be positioned relative to each other in a simplified two-dimensional latent space, commonly used in machine learning and data analysis to uncover relationships between entities or features. Let's break down what you're seeing. Understanding the latent space diagram axes, D1 and D2. These axes represent dimensions of a latent space. Each dimension captures certain features or characteristics of the data. In this context, D1 and D2 could represent different underlying features that differentiate these entities, like market focus, technology used, or business model aspects. Vectors. Each vector, arrow, points from the origin to a label, EVPN, VPLS, Microsoft, Amazon, representing how each entity is positioned in this two-dimensional feature space. The direction and length of the vector can imply how strong particular features, represented by D1 and D2, are in each entity. Comparative positioning. EVPN and VPLS are shown closer together, which might suggest these technologies share similar characteristics or are related in the context captured by D1 and D2. Microsoft and Amazon are also depicted closely, possibly indicating that in aspects represented by these two dimensions, their business models or strategies are similar. Practical implications. Feature interpretation. In real scenarios, each dimension in a latent space would represent a conglomerate of features like user preferences, product characteristics, etc. Analysts might interpret these dimensions by examining which variables are most influential along each axis. Entity relationship. The proximity of entities in this space can help in understanding relationships, such as similarity in products, market strategies, or customer bases. Dimensionality reduction. This plot might be the result of a dimensionality reduction technique, like PCA or TSNE, commonly used to simplify high-dimensional data into 2 or 3 dimensions so that they can be easily visualized and analyzed. Applications. Market analysis. Companies like Microsoft and Amazon being close in this space could be used by analysts to study competitive strategies or market positioning. Technology similarity. Grouping technologies like EVPN and VPLS may help in understanding technological trends or in developing products that cater to related needs. Conclusion. This type of visualization is an effective way to conceptually understand and explore the relationships and similarities between different entities or features in a dataset. It provides a graphical interpretation that can support decision-making and strategic planning, especially when dealing with complex or multidimensional data.
All right, that makes sense. So there are fundamental concepts to remember as they serve as the basis for many NLP use cases. In the practical use cases section of the book, we will see various applied examples of NLP, natural language processing, to deal with log messages and configuration data. We will apply all the techniques reviewed above, such as encoder-decoder architectures, building dictionaries, tokenizers, eliminating stop words, clustering texts, identifying texts, and predicting texts, as well as building a language model. Key takeaway: the main challenge in NLP is data representation. Multiple options exist. You must evaluate your use case, what your goals are, and select the adequate numerical representation for your natural language data. Okay, so the next section is large language models, LLM. This is ChatGPT, as far as I understand, is an LLM. This is kind of the flavor of the day. All right, and I need a quick break. I'll be right back. All right, I'm back probably got at least another. Well, I've probably got at most another 15 minutes, but I think that's enough time. So speaking of language models, this has been one of the critical areas of innovation in NLP in the last few years. Large research branches from big tech companies and startups, Google's DeepMind, OpenAI, Meta AI, etc., have produced breakthrough innovation by building and training the so-called large language models, LLM. Examples include GPT-3, which is the technology behind ChatGPT-3. ChatGPT-3 is like the name of the product. It's kind of like the word car versus Toyota. You know, a Toyota is a type of car. ChatGPT is a type of GPT-3 based AI technology. Google's Switch Transformer or Meta AI's OPT 175B. And let me just fact check that quick. So is it fair to say that GPT-3 is to ChatGPT as engine is to car? And sorry, there's issues with my audio. I will fix that.
Making it a significant component of the broader AI landscape.
There you go. So,
ChatGPT is to GPT-3. ChatGPT is an application of GPT-3 tailored specifically for conversational use. It leverages the underlying capabilities of GPT-3 to engage in dialogue.
all right, so it's a fair analogy. Let's hear what it has to say in full.
Yes, that's a fair analogy. Let's break down this comparison to understand it better. GPT-3 is AI. GPT-3, which stands for Generative Pre-trained Transformer 3, is a specific model developed by OpenAI. It's an example of advanced artificial intelligence, particularly in the field of natural language processing, NLP. GPT-3 is one of the most powerful models for generating human-like text, making it a significant component of the broader AI landscape. ChatGPT is to GPT-3. ChatGPT is an application of GPT-3 tailored specifically for conversational use. It leverages the underlying capabilities of GPT-3 to engage in dialogue, answer questions, and interact with users in chat-like format. Essentially, ChatGPT is a specific implementation that uses the GPT-3 model to power conversational AI. Engine is the car. An engine is a fundamental component of a car, providing the necessary power for the car to operate. While a car consists of many other parts that contribute to its overall functionality, like wheels, steering system, and body, the engine is critical as it drives the car's movement. As engine is the car, just as an engine powers a car, GPT-3 powers applications like ChatGPT. The engine itself is a complex and crucial component, but it needs to be part of a larger system, the car, to serve its practical purpose. Similarly, GPT-3 is a sophisticated tool that can be part of various applications, with ChatGPT being one of them, aimed at specific uses. In this analogy, GPT-3 is like the engine, a core technology that drives the operation. ChatGPT is like the car, the actual application that people interact with, powered by the technology, GPT-3. This comparison effectively illustrates the relationship between a powerful underlying technology, GPT-3, and its practical implementation, ChatGPT, a user-facing application, much like the relationship between an engine and car.
All right, so moving on. These are huge models with trillions of trained parameters. They are not only out of reach for most organizations to build and train, but also even for inference because of the amount of resources required to run them. By exposing an inference API, it is now possible to take advantage of these large language models in various applications and use cases via API instead of running the model locally. This has triggered a new era in AI/ML technology consumption where models are consumed as a service. Zero/one-shot classification. These large language models have been trained with enormous data sets, entire Wikipedia, online books, etc., etc. They enable a wide range of use cases. In NLP, one of the most common goals is to use a model to classify texts on a particular set of classes. Traditionally, classification tasks require a model to be trained with a labeled dataset, as we have learned, and then you can make an inference with new observations. If you remember, we introduced the idea of Siamese networks and how they were trained to build a similarity function. Once they have been trained, they could be exposed to two pictures they have never seen and tell us if the pictures correspond to the same person or not. A similar principle now applies to large language models. These large language models introduced above have such broad knowledge captured that can be used to enable what is referred to as zero-shot classification, sometimes also referred to as one-shot classification or few-shot classification. There we go. The goal is to be able to classify a text as belonging to a set of categories like you would with your own model. Here the approach is different. The model can receive an input as text and also a class or a set of classes, which are also pieces of text themselves, maybe shorter, like a word.
The diagram you uploaded illustrates the concept of zero-shot classification using a large language model, LLM, such as GPT-3. Let's break down what this diagram depicts in the underlying process. Components explain, text to classify. This is the input text that needs to be classified. It appears to be some kind of error log or diagnostic output suggesting a problem with the system or software. Classes to classify. These are the potential categories or classes into which the text can be classified. In this case, the classes are hardware problem and software problem. These categories are predefined and are used to interpret the output of the classification. LLM, large language model. The LLM processes the input text and performs classification based on its training on a wide range of text data. It uses its understanding of language and context to assign the most likely category to the input text. Latent space. This is a conceptual representation of the high-dimensional space where different features of the data, words, phrases, context, are mapped.
Right.
In the diagram, this space is shown in 2 dimensions for simplicity. The vectors, hardware problem, software problem, and the question mark, which likely represents the input text, show how the LLM distinguishes between different categories based on the features extracted from the text. How zero-shot classification works. Understanding without prior examples. Zero-shot classification involves classifying data into categories that the model has not explicitly seen examples of during training. Instead, the model uses its general understanding of language and context. Semantic understanding. The LLM leverages its pre-trained knowledge to understand the meaning of both the text and the categories. It evaluates how closely the text matches the concept of each category based on its semantic understanding. Projection in latent space. The model projects the text and the categories into the latent space and measures the proximity or similarity between the text representation and each category's representation. The closest category in this space to the text is usually chosen as the classification output. Practical application. Support systems. Such a system can be employed in customer support or IT departments to automatically classify the nature of issues reported in logs or customer complaints, directing them to appropriate resolution teams without manual intervention. Enhancing automation. By using zero-shot classification, organizations can automate many decision-making processes, reducing the need for extensive retraining of models when new categories or topics emerge. The diagram effectively encapsulates how advanced language models can infer and classify text into specific categories based on semantic understanding, without needing direct training on those specific categories. This capability makes LLMs particularly versatile and powerful in handling a wide range of NLP tasks.
Alright, so if you remember, the ability of these models is to push input data into a latent space that provides a more semantically significant comparison among different inputs. There we can compare the latent representation of the text to classify with the latent representation of the desired classes and pick up the one whose distance is lower. The model can project any text into the latent space and provide a semantically accurate view of their distance. Therefore, without having trained the model specifically for the text or classes provided, we could do a classification much like if we had actually trained a dedicated model. It works because the large language model can project in that latent space, latent semantic space, both the text and the classes. It has been trained with sufficient data such that in a new task it was not explicitly trained for, it can perform very well. In the practical sections, we will see examples of the applicability of zero-shot classification to classify syslog messages. We will also see practical examples of using ChatGPT and its potential to networking and cloud infrastructure management. All right, so the next section, we're getting into the good stuff. It looks like a strategic view of deep learning for network and cloud AI ops. So with that, that's going to have to be in another video. So thanks for watching, and stay tuned for the good stuff.